If you're given a number n, how can you tell whether it is prime? This idea is called primality testing, and that's what we want to talk about in this video. There is a very obvious way to go about this, given the definition of prime number, and that's what I want to go over in this video. But what I ultimately want to do is convince you that this doesn't work very well if you have a very large number that you're checking. Okay, so the obvious approach is called trial division. Just check all the numbers that could be factors of n and see if any of them are. See if they go in evenly, right? So that's the obvious thing, because that's the definition of a prime number. Prime number has no factors other than 1 and itself. So what you can do is check all the numbers in between. You can check everything from 2 to n minus 1 and just divide, see if it goes in evenly. So that's great. One improvement we can make, though, is we don't actually have to do all these numbers between 2 and n minus 1. One improvement is we actually can stop a lot earlier than n minus 1. So as an example, let's think about the number 30. 30 is obviously not a prime, but let's think about its factors, right? So 1 and 30, of course. 2 and 15, 2 times 15, right? 3 and 10. 5 and 6. And what I want to point out is that if you look at the square root of 30, the square root of 30 is, so square root of 25 would be 5, the square root of 36 would be 6, so this is somewhere between 5 and 6. It's 5 point something or other. And if you notice, in every pair of factors, one of the numbers is less than the square root of 30, and one of the numbers is greater than the square root of 30. And that would make sense, and that would always be the case no matter what number you were doing, because if both of the numbers were less than the square root of 30, then when you multiplied them, you would get less than 30. And if both of the numbers were greater than square root of 30, then when you multiplied them, that would be more than 30, right? So you always have to have one that's less than 30 and one that's greater than 30. With the one exception, if you have a perfect square, then of course you could have the square root exactly twice, right? That times itself. So for example, if we were doing 36, we could have 6 times 6. But my point is, you actually don't have to go all the way up to n minus 1. You can just go up to the square root of n, because you'll find one of the pair of factors if you go up to the square root of n. And you don't have to check the other ones. Okay. So that's actually a good time saver, to only go up to the square root of n. And if you were programming a computer to check numbers whether they were prime, you would do this. You would only need to go up to the square root of n just to save time. Other things you can do are simple things like after 2 you do not have to check even numbers. So you can skip even numbers after 2, right? Because if 2 doesn't go into it, then an even number, any other even number won't go into it either. And so often people would do that if they're doing trial division. They would check 2, but then go 3, 5, 7, 9, etc. And you can go further. I won't write it down, but after you check 3, you don't have to check multiples of 3. And after you check 5, you don't have to check multiples of 5. So you can continually improve this, but eventually it gets a little cumbersome and ridiculous. But yeah, you can do that. All right, so trial division is a basic idea for checking whether a number is prime, and we can do some basic improvements to make it go a little bit faster. However, I want to now show you that even with these improvements, even with the square root of n thing, and even with skipping even numbers, this is not going to be feasible if you have an extremely large number. So let's think about a 1,000 digit number. So that would be a number that was roughly 10 to the 1,000, right? Okay, so the square root of that would be 10 to the 500, which is a lot less than 10 to the 1,000, but still pretty big, right? And like I said, we could skip all the even numbers, so we could do half of those. So we would be wanting to check 10 to the 500 over 2 numbers. We'd have to do that many trial divisions. Okay, could a computer do that? Let's assume that we have a computer that can do, a reasonable number would be like 5 billion operations per second. So let's assume it can do 5 billion divisions per second. That would be pretty good. Okay, so that's 5 times 10 to the 9th. All right, well then, 10 to the 500 divided by 2, operations that have to be done, divided by 5 times 10 to the 9th operations per second. When you work that out, that actually comes out to 10 to the 490 seconds. So, still a very long time to do it. In fact, how long is that really? If you change units, this is like 3 times 10 to the 482 years. Or, using the age of the universe as 13.8 billion years, this is 2 times 10 to the 472 ages of the universe. Okay, needless to say, you're never going to use trial division to check a 1,000-digit number for primeness. It is just not even close to being feasible. And even if we only had a 100-digit number, something like that, which is way, 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 way smaller, you'd still run into a completely infeasible situation to have a computer that could check all these numbers. There's just too many numbers to check. Okay, so I hope I've convinced you of that this is not the best way to see if a number is prime, and so we need other ways to do it. And so in other videos, we'll investigate certain properties of prime numbers that will allow us to do a better job, a quicker job on attempting to see if a number is prime.